All right, so welcome back to this channel. So in the last video, so in this video, I think over the past few videos, we have been exploring natural language processing, different techniques, different ideas, different architectures, different practical approaches, uh, especially in the area of natural language processing. Uh, you know, these are the types of language models. There has been release of many powerful language models that have been able to accomplish just amazing tasks, right? We are able to, so these language models are very exciting and very interesting, and they can achieve so they can actually reach the performance of human. They could reach the human level performance, which is pretty wonderful. So as there is a lot of work and attention, the performance metric, so there has been like huge amount of increase in the performance of the model, right? As there is like a lot of data, as there is a as there are like lots of data online due to internet. These language models are very powerful. These are becoming very much more powerful and much more human like. So as there is a lot of data, so as there is a need of much better performance for language models, this is the best time for us to make these attention models or make these language models much um, time effective. So make the model fast and also memory efficient, so such that they don't like have to store lots of data, and they also should be fast. So that is the main thing when it comes to training. So yes, there has been improvement in GPUs. There has been tremendous work in GPU, and a lot of work in making this attention fast. At least in this time, there has been a lot of work uh, done by researchers to increase the speed of transformers. So a lot of work is using. So the main thing a lot of research papers nowadays are doing is to make the models um, use the power of parallelization. So GPUs are known for parallelized computing. So computing two values, like let's say at the same time. That is why GPUs are known for. So in order to use this power, a lot of changes have been made for the recent architectures. So there has been a lot of work has been done, and this is one of the famous work, flash attention. So we'll be covering that. Paper was released last year, 23 June 2022. So we will be covering this paper, what this actually proposes. Transformers are slow and memory hungry, or on long sequences. Of course, they are. So before that, I just want to, there is a lot of GPU stuff. There is a lot of hardware stuff that is explained in this paper. So the thing I want to tell you is the modern day transformers can perform calculations. So they are the modern day transformers, or the modern GPUs are getting better and better at performing calculations. So they can perform calculations much better. For example, matrix multiplication, they could perform matrix multiplication very fastly. So that is the specialty of modern day GPUs, like NVIDIA RTX and all that. So these algorithms, so these approaches tend to use that ability, or so tend to use that feature of GPUs, that the modern day GPUs are better at computation rather than memory storage. So therefore we will before going to this paper, keep in your mind that GPUs are faster at computing rather than storing and writing and reading to the memory. So one of the main approach that has been taken, or one of the main changes that has been done in this, is recomputation. So computation, so they'll increase the number of computations they have to make and decrease the amount of reads and writes. So like, for example, there will be memory, rather than just reading and writing for different operations, and maybe for back propagation and all that, we will recompute it again in the back propagation also. We'll be covering that also. Right, we'll also be covering that. So so this is the so we'll essentially like we'll be carrying all of the operations in like the same time and having blocks and all that. So we propose flash attention, a new attention algorithm that computes exact attention with far fewer memory access. Our main goal is to avoid reading and writing the attention matrix to and from HBM, right? So they'll avoid reading and writing to the memory as many times as possible. So they'll avoid reading and writing. So they'll decrease it as low as possible, reading and writing to the memory. Right, this requires computing the softmax reduction without access to the whole input. Right, so there is also one approach in which we will not compute softmax. So softmax is used a lot in transformer architecture. So we'll, rather than like performing softmax on the whole data, we'll perform it step by step, creating blocks, something called blocks, which is pretty much used in this paper, right? And make several passes over input blocks, thus incrementally performing the softmax reduction, also known as tiling. So this is tiling, in which we'll incrementally perform softmax over block by block in the input data, right? We store the softmax normalization factor from the forward pass to quickly recompute attention on chip in the backward pass. Right, so this is one thing that that is that is pretty intuitive, and that does make sense. So for example, so let's say there is a normalization factor, or let's say there is an input, right? You go to the forward pass in the attention. So you're gonna have like forward propagation and backward propagation. If you are not aware of the notation, forward propagation is predicting the value, backward propagation is updating the value based on the given loss function. So after forward propagation, we are going to compute a value, right? We are going to compute a value, let's say the attention matrix or anything, right? The attention matrices, the outputs of each like layer and all that. So in the backward propagation, rather than just writing this data to the HBM or to the memory, what we'll be doing is we are just going to recompute it in the while back propagation. So most of the values we will be recomputing them again while performing the backward propagation. And that is pretty intuitive because, of course, modern day GPUs are better at computation rather than storage. So that is one thing. The intermediate attention matrix from HBM. We implement fast attention in CUDA to achieve fine-grained control over memory access to fuse all attention operations into one GPU kernel. Even with increased flops due to recomputation, our algorithm both runs faster and uses less memory, right? Linear in sequence length than standard attention, thanks to the massively reduced amount of HBM access. So there is going to be a lot of flops. Flops is nothing but the number of. So flops is a metric to determine the number of calculations that took place. So flops is nothing but it predicts the number of, or it generates the amount of or it is just a value determining the amount of calculations done in an algorithm. So here in flash attention, there is going to be increased flops because we are going to do a lot of computation because of recomputation also. While in the back propagation, we are going to recompute all the values. So there is of course going to be increase of flops, but the algorithm runs faster. Why? I will state the reasons. Modern GPUs are better with computation rather than just reading and writing to the memory. So there's going to be, I think, a hierarchy, like what is fast and what is not in modern day GPUs. So so and also the so the time complexity is like linear in sequence length. So the amount of, so if sequence length increases, the time also increases. So it is like big O notation. So it just determines the amount of fastness of an algorithm based on the increase of the size of the input. So we analyze the IO complexity of flash attention, proving that it requires O of n squared d square m minus 1. Okay, we'll just leave that for now. Yeah, so far again, flash attention requires many times fewer HBM accesses, as showing that no exact attention algorithm can okay. Yeah, so we'll just leave that. So we also that flash attention can serve as a useful primitive for realizing the potential of approximate attention algorithm by overcoming their issues with memory access overhead. Yeah. So so we don't have like faster model training. I think in this paper they have used this techniques or use this algorithms on the BERT model, right? We train BERT, so they train our BERT model with the BERT architecture, um, right? And then the higher quality models. So flash and instant scales transformer to longer sequences, which improves equality and enables new capabilities. Of course, because we are dividing the input in blocks, so we're going to have like input, we're going to divide it blocks and perform the attention for each block. So therefore, of course, longer sequences can be okay. Enable the first transfer that can achieve better than chance performance on PathX challenge and all that. Okay. So this is the hardware performance. I think so they have something called kernel fusion, right? I think it is a metric that they have used. So it's a method they have used. So so we just read through what that is. The time taken by the operation is determine how many arithmetic operations are there, while time accessing HBM is smaller. Okay, so we'll just leave that. We have already covered that. So the time taken by the operation is determine the number of memory accesses, while time spent in computation is much smaller. Okay, memory bound. The most common approach to accelerate memory bound operation is kernel fusion. If there are multiple operations applied to same input, the input can be loaded once from HBM instead of fuse it and instead of um, multiple times of for each operation. So what they have told in this paragraph. So I have spent a lot of time just reading that. So kernel fusion. So they use a method called kernel fusion. It is nothing very simple. It is very simple. Don't think it is don't think that it is very complex. So the thing is, while performing attention, right, we have to do like a lot of calculations and all that. So in the standard attention, in the standard attention implementation, what we'll be doing is we'll be performing each calculation and then writing it back to HBM, right? And then we are going to read it back again for other calculations. We're going to write it back to HBM. So we are going to perform a lot of reading and writing operations in the standard attention architecture or implementation. So we are going to like read and write it to them memory and all that. We're going to save values. We're going to get them back and perform the operation and write it back to HBM again. So this amount of reading and writing to HBM, right, decreases or increases the speed of the model. So the speed of the model will decrease because we are going to write and read a lot of to HBM. And of course, modern GPUs are faster with computation and less faster with reading and writing memory. So therefore, using kernel fusion. So kernel fusion is a method in which we'll just read from HBM once and we'll perform all the operations at the same time. So we'll have like one huge function. We're going to perform all the operations at the same time, all the required operations, attention operations, and then we're going to write it to the memory once only. Right? We are not going to read and write many times. So we're going to remove the we're going to decrease the number of times we read and write to the HBM as far as possible. So that is the idea of flash attention or kernel fusion. Sorry. So this is the standard attention implementation, right? So we just have like three metrics QK and V. We load the QK blocks from HBM. Compute S, we write S back to HBM. So as you can see, this is the problem that we are talking about. We are going to create matrices in HBM in memory, and we are going to load QK from HBM. We are going to compute S. We are going to write S back to HBM. Right? We are going to read S again from HBM. I think we are going to perform a lot of read and write operations, and we're going to compute P. We're going to softmax and write it back to HBM. Right? Even for softmax operation, we're going to write it and read it. Just a lot of time taken here. And we're going to load again from HBM, compute O and write O back to HBM and return O. So yeah, there is a lot of HBM there. We're going to write and read a lot of times from HBM. So or memory. therefore, it is no surprise that the model is very slow, or it is pretty slow. Right. So now they introduce flash intention, and they introduce an algorithm which we are going to cover. So I'm not going to cover the mathematical like softmax part and all that. We'll go to the pseudocode like maybe very high level. But given the inputs Q can V in HBM, we aim to compute the attention O and write it to HBM. Our goal is to reduce the amount of HBM access. Right. So that is the main thing of this paper. So this is the pseudocode. This is the pseudocode that I wrote, just like above, in the standard transformer. So we'll have QKV vectors in HBM, right? And then we're going to create blocks, right? We're going to create bunch of blocks, right? And then we are going to have one O. So O is going to be like the output that is going to have all the QKV vectors. So we'll get the Q, and we are going to divide this Q into many blocks. So we're going to divide into BR number of blocks, Q1 to QTR, of size BR times D, and divide KV into TC, and by DC BC blocks, so up to K, TC and all TC. And we are going to divide O into TR blocks. So this is the output. And what we are going to do is we are going to loop through TR. Yeah. So we are going to loop through all the words. So we are going to loop through all the words, of course, all the queries, all the keys and values. And we are going to load the values from HBM. Right, we are going to load it from HBM. Just look at the decrease in the amount of times we like call and read to HBM, right? And we are going to load QK vector, QOLM vectors. We are going to on chip. We are going to perform this, and then we are going to perform this, and we are going to perform this, and then directly add that to HBM. So we're going to not do a bunch of read and write accesses. So first we're going to calculate the normal attention. We're going to multiply Q and K, and then we're going to do this. So this is nothing but the splitted softmax. So we're going to have like splitted. So we're going to essentially like split it and new softmax that I've just like I said. So there's one article that I found very helpful while understanding this paper by Alexa Godek. He has a very famous YouTube channel, and I have personally learned a lot from him. So so he has wrote this article on flash intention. If you want, please check it out. I might not cover the complexities here, the mathematical complexities. All right. So I mean, like, I think we'll just go through the implementation of flash intention in the next video. Maybe I'll try to, or one of the future videos we are going to cover the implementation. They have this implementation, and the implementation is like pretty complex. So there are like at least 500 lines of code in each of the file, I think. So there is a lot like huge amount of code. We are going to go through that in probably next video. So yeah, so we're going to perform all these operations on chip SRAM, and we are going to use SRAM as much as possible and decrease the use of HBM, right? So that is the thing. Yeah, so that is essentially it. We'll do QK vectors multiplication. We have V here, I think somewhere. Yeah, we should have V somewhere. Yeah, so we are going to perform all these operations, and then yeah, so and then we are going to and then one more extension is that we are going to use blocks parse flash attention, in which we are going to divide the inputs into blocks, of course. And what we are going to do is, so generally language models do not give, so there is no need of attending words now to the words that are in very past. For example, there is a, let's say, huge document. So let's say there is a huge document with like 10,000 or 100,000 words. There is no need to attend each word to every other word, because chances are that that word does not carry huge amount of attention or huge amount of influence on the let's say last word. So the first word does not carry a huge amount of attention in the last word. So therefore, using this tendency of language, we are going to divide this input into blocks and then perform attention on each block. So each of course we're going to have like huge blocks, huge tokens, but we're going to perform attention on these specific blocks. So that is the main thing. So given a predefined block sparsity mask, we can easily adapt algorithm 1 to not only compute the non-zero, so to only compute the non-zero blocks of the attention matrix. And one more thing is that we are going to like we're going to like skip skip some blocks. So we're gonna have like bunch of blocks, right? So using block sparse attention, so that is a new technique. We are going to like skip some parts or skip some blocks, rather we just not compute attention on some specific blocks that we don't think are very good, or that does not like follow a specific criteria, right? So that is the idea of block sparse attention. And I think that's it for this video. I think that's it for this paper. And yeah, a bunch of references and all that. Yeah, they also shared like related work, sparse training, efficient transformer. I think that's it for this video. I think this is a very introductory video. I have not covered everything in detail, but hope you have understood the basic thing of flash attention. Even I have like not spent much or enough time on this paper. I think I have to like maybe go through the implementation, all that. So in the next video, we are going to go through flash attention implementation. So there is like huge amounts of code written, 1113 lines of code just in this one file. Sorry, no, 1160 lines of code just in this one file. And like let's see how many here. Yeah, 197 lines here. And let's see here, 792 lines here. So yeah, there is a lot of code that we have to go through, but I think I'll just cover the main parts of this code. I'll try to provide as much as context as possible to that code in the next video. So thank you for watching. I'll see you in the next one.